So today's question is middle of the linked list. We are given the head of a singly linked list, and we need to return the middle node of the linked list. And if there are two, we need to return the second middle node. So for example, this list has an odd amount of nodes, so there will be one middle node, and this one has 6, so it's even. So we return the second middle node, which is 4. So the more naive approach to this problem, or before I go any further, does anyone have any questions? Everyone understand the problem? Cool. Okay, so we need to find the middle. The more naive approach to this would be to count up the number of nodes and then get the middle rounded up in the case of an even amount. So for example, if we have 1, 2, 3, we would count up the amount of nodes. We have 1, 2, 3. And to get the middle, we would take 3 divided by 2. Which gives us 1.5, and round that down to get a valid index. Round it down to 1. Or, sorry, round it up to 2 and get the second node starting at 1. Or we could round it down if we're going to 0 index these indices. So either one. Let's say we round it down though. So starting here, we have the 0th index and the first index, and this is the middle. And if we added on a 4th node, we count these up, 1, 2, 3, 4 nodes, 4, and then divide that by 2. Doesn't matter how we round it because this is still an integer, and we get the second index. So 1, 2, 0, 1, 2, which is what we want. We want the second middle node, which is perfect and a good reason to 0 index. If we 1 index, we would be getting the first one. So let's implement that solution real quick. So we're given the head, and we need to loop through it. So we'll make a pointer to the head. And while our current node is not equal to null, we are going to move it forward. Set cur to cur.next. We know for a fact, since we just checked that, oh, well, I think that's fine. We can say cur can also be null. So this can be either null or a list node. And then let's make a variable to store the length. Length is 0. And then while we do this, we do length plus equals 1. And to find the middle of the linked list, we can say let middle is equal to the head and loop through. So let I equal 0 and while, or not while, sorry. While I is less than length, then we are going to increment. and set middle to middle.next. And we know for a fact here that middle is not null at this point because we've guaranteed, or we've already counted this. So we want to do length, but do we want to floor it? I am not sure. What did we say we wanted to do? So if we have 3 divided by 2, yes, we want to floor it because then we have 0, 1. Perfect. Math.trunc does the same thing. I'll do it just because I mix it up sometimes with math.min. And then finally, we return middle. Let's just say this can't be null, because it can't be null. So we get lots of non-null assertion. Perfect. Anyone have any questions before I run this code?
Yeah, so why are we setting middle to head?
Instead of using up head,
Is it because we've already... Oh, okay.
we need at least one pointer that we store the head in. So like for cur, here, we are looping through, and if we set head to head.next, then head would be a pointer to null at the end of this, which wouldn't be
Gotcha.
helpful. And then here, we could use head to find head, but this is a more descriptive name, and we aren't changing head. So if the user of this function wants the middle node of their list, but they don't want us to use up their list or change the head pointer, then this is better.
Gotcha.
Yep. I typically would not expect it to do that. It feels kind of weird to say, or like call a middle function and then your head pointer is now completely different. Okay, so let's run the code. See if I made any mistakes. Looks good. And works. Any questions before we move on to the next approach? Okay, so while this works, and it's not space intensive either because we're just storing a number, we can do a little bit better. We can use a specific algorithm to not have to actually loop through it twice or store any indexes. And that algorithm is the tortoise and hare algorithm. So let's make this slightly longer. We have a slow pointer and a fast pointer, and we iterate through. So each loop, our slow pointer moves forward 1 and our fast pointer moves forward twice. And by the end of our list, the fast pointer, or when the fast pointer hits null, or the next on the fast pointer hits null, the slow pointer will be at the middle because that's the halfway point of the list. So starting our slow and fast pointer here, we first move slow pointer forward and the fast pointer forward too. And then we move slow pointer forward again and the fast pointer forward too. So fast pointer is now at null, so we end. And our slow pointer is at the correct middle, the second middle node. So our condition for this is when fast is equal to null right now. But what happens if we do it with another node? So starting off again, we move slow forward to here, move it to 2, move our fast forward 2 places, then move our slow forward and our fast forward 2. So it should end right here. If we continued checking to see if fast was null, we would run into a runtime error because we would move forward or fast forward once to null, and then null doesn't have a .next property, and that would throw an error. So we also need to make sure to check for when f.next is equal to null. And if we look at this, the next pointer for the fast pointer is null, so we would end it here. And this is the middle. Does that make sense for everyone? Cool. So let's implement this one. So we have a slow pointer, which is equal to head, and a fast pointer that's also equal to head. And while fast is not equal to null, as well as fast.next is not equal to null, we are going to iterate through the list. So slow is equal to slow.next, and fast is equal to fast.next.next. And we've guaranteed that these can't be null because we said fast is not equal to null here, and fast.next.next is not equal to null. And since the slow pointer will always be behind the fast pointer, we know that's also not equal to null. So for the first loop, they are equivalent. And then moving on to the next loop, fast will be ahead of it. So we know fast will be, this next will never be null either. I believe it might be, actually. Let's check. How long can this be? So the list is at least 1 long. If it is 1 long, what do we do here? So at this point, our fast.next would be equal to null, and we would end. So slow will never be equal to null once we're in this list, because this requires at least 2 length of our list. So I think this is safe to say. And then this one could be null. So we can type this one as list node, and this one as list node or null. and this should be fine. This one can possibly be null, but that's okay. And then we just need to return the slope pointer. Any questions on any of that?
What does the colon mean on lines 8 and 7?
Okay, those are for type annotations for TypeScript. So I'm just saying this should be a list node, and this one can be a list node or null.
Okay, cool. Thanks.
Yep. Just helps out quite a bit with all of the possible nulls that are here. I don't need it for the... Oh, sorry, go ahead.
Sorry, I thought she was talking about the colons at the very end. I was just gonna say, like, you can put that or you can choose not to. Like, you know how...
No, I did mean after slow and fast, those ones.
Oh, the semicolons. Yeah, those ones
No,
are...
no, not the semicolon. Sorry. You answered it already.
Okay.
Oh, okay.
Yes. Thank you, though.
Yep. Typically, these are inferred. Like for this one, it gets inferred correctly because it just takes the type of head. But for fast, it can be null, so we need to change it. And then I just have slow for consistency. Cool. Any other questions? Okay, sounds good. Let's try it out. Nice. And then here, just to go over our time and space complexities, for our first solution, it is O of n or O of n time complexity in O of 1 space, because all we're doing is storing one extra. We're storing our length, which is constant. We aren't storing any more lengths for the length of the list. And then for this one, it's O of n space or O of 1 space, sorry, and O of n time as well. Because all we're doing is storing 2 pointers, and that doesn't change for the size of the list. So whichever one you pick is up to you. Depends which ones you like better, but there may be cases where it's better to do slow and fast pointer approach, but this might not be the problem for that. Just good to have seen it before, I would say. Oh yeah, and here the non-null assertions are good or okay, because if my assumption is wrong and it can be null, like for example, if I remove the fast.next is not equal to null, and I make the assumption that it can be null, then it will throw a runtime error. It might return it for if I assume that this one couldn't be null, then it could return null though. So maybe not. So in your production code, you might want to actually do a null check. Or you can just write tests and you'll have the safety you want. Any questions on anything so far? Gonna throw the code in the chat. Oh, are you asking what the exclamation mark is for after slow? Okay, so that is a non-null assertion operator. We are asserting that the value is not nullish, so we're saying slow is not null at this point. And if I remove it, I guess that's fine. It doesn't need it. Oh, okay, I only need it at the end. Yes, it's a TypeScript thing. So I'm telling it that this is not null because we said that slow can only be a list node. So we're saying we know more than TypeScript and this cannot be null. Otherwise, if we didn't want to do that, we would have to check again. So for things like this, we have guaranteed that fast is not null. So this one's good. And fast.next is also not equal to null. So we are happy to put it in there. Someone's asking why we have to tell it everything. We have to tell it that because it's possible that there's more code up here and we're just like fast is equal to null. And then at this point, these non-null assertions would be incorrect. But we know we didn't do that, so we're okay. But if someone decided to do that, yeah, that's a more contrived example, but it's possible. You'll also see it in GraphQL. So it's not called non-null assertion. I'm not sure what it's called, but you essentially assert the value is there. So if you have a string and you put a bang there, then you're saying there is a string in my array. Or if you say bang for the array, you're saying the array is there because it's optional otherwise. How did I learn the solution? I memorized the solution pretty much. It's just a very specific algorithm that is useful in some other situations. Like in a problem we did before, I believe, linked list cycle. So finding where the cycle starts, this algorithm's also useful there. I feel like algorithms are more, you can memorize the algorithm and it's okay until you need to edit it a little bit. So you need to know how to change it up a little. But like if we wanted to find the third, instead of the middle of the node a third of the way through, we could probably just make fast.next.next.next, and then it would be 3 times faster. So this one's a somewhat easy to change algorithm. We just need to know where to apply it and how to change it to our needs. Yeah, someone's in chat saying starting off with memorization is the way. I definitely agree with that. If you're confused with this problem, I'd recommend going on LeetCode, finding the problem and looking at similar ones, or going back to that other one we did prior. Let's see where that one is. Linked list cycle, yeah. So linked list cycle also uses this same approach. It is changed a little bit more. there's another thing in here. It's not just finding the middle. Well, technically there's no middle because there's a cycle, but it uses the same slow fast pointer algorithm. So I would recommend trying that one out. To practice the algorithm. Any other questions? And also there's like 0 chance you're going to be able to find out that algorithm on your own without just looking. So if you get stuck after you give it a good try, make sure you look at the answers and try to understand them. There's like a big mathematical proof to why this one works for the linked list cycle problem, but you don't need to understand the mathematical proof to use the algorithm. You just need to know it works. Okay. If there's no more questions, I'm going to end the recording here. I'll be glad to answer any questions after the recording as well, though. The next question we have is maximum depth of a binary tree.